If you have images taken with different seeings, doing aperture photometry on these faint sources is non-trivial. You have to make sure that you're measuring fluxes that correspond to the same part of your sources. One way that we've been exploring in Leiden is to try to standardize the images by making Gaussianized point spread function images. So if you imagine that you want to measure an intrinsic flux of a galaxy, this is an integral over the intrinsic flux of a galaxy with a Gaussian weight function. This is basically like the KSB moments, but with the zeroth moments. This is an intrinsic property of the galaxy. You cannot measure that directly because you have seeing, but if you imagine that you have an image of this galaxy taken through Gaussian seeing with a Gaussian PSF, then you can measure something like this, which is a Gaussian weighted flux with a weight function small w in the presence of a Gaussian point spread function with a particular width, q in this case. And so it's a double integral. This is the seeing-convolved galaxy, and then this is your photometric weight function. And it's easy to show by swapping these integrals that this quantity is related to the intrinsic Gaussian width, Gaussian photometric moment through a very simple relation here. And so what that means is that things like this are actually accessible observationally, even though it's an intrinsic property of the galaxy. They're accessible observationally from images in which the point spread function is Gaussian. And so what we figured out is how to take galaxies with a particular well-measured point spread function and homogenize this point spread function and turn it into a Gaussian. And then once you have that, then you can actually do this kind of aperture photometry on the different images and get consistent fluxes, which really represent the same weighting of the galaxy intensity distribution in the different wave bands and give you the basis for accurate photometric redshifts. And this actually works. So this is an example from one of the CFH TLS images. This is 1 square degree field. These are vectors which show you the ellipticity of the point spread function. And you see that you can also not only completely round the point spread function with this Gaussianization technique. This is the residuals at a resolution 5 higher. So you basically see you smooth away all the large scale structure in the point spread function shape. But if you make a plot of the size of the point spread function, you also see that the 20% variation that you get from the center to the corner in a typical CFHT image is also completely corrected away. So you can do this. And as Catherine showed, this actually works and helps to improve the photometric redshifts that we're able to get out of the CFHT considerably. Then let me make one remark on getting very accurate photometric redshifts. In the surveys people are planning for the far future from space to get the kind of measurements on dark energy equation of state that you can get if you look purely at the statistical weight of such a survey requires that you contemplate getting photometric redshifts to about a part in 1,000. That's the kind of differences in the photometry that you would need to get the kind of differences in W that people are trying to find. And that's incredibly challenging because we're thinking about filters with lambda over delta lambda of maybe 10, 5 or 10. And so that's a huge factor to get to that improvement. Of course, this is not for every single galaxy, but this is the statistical average. This is the level of systematic errors that you want to be able to control. And so let me make one cautionary remark here. I'm not saying it's impossible, I'm just saying that I'm worried about it. And that's to consider my own private galaxy spectroscopic survey. This is the LSG survey, the ludicrously simple galaxy survey. And this is a survey in which all the galaxies in spectra like this. And they're not actually too bad a cartoon from real galaxies. So it's a simple spectral break with an absorption line at the base of the break. Right. And you can play with two parameters. You can play with the height of the break, and you can play with the depth of the line. So let's put a photometric redshift survey on top of this. Here are 3 filters. One this side of the break, one that side of the break, and one covering the break and the absorption line. And let's see what galaxies like this look like in a color-color diagram as you redshift them. And this is what they look like. There's 12 different galaxies plotted here, going from low to high redshift. And there's different families, different choices for the size of the break and the depth of the spectral line. These are the 2 possible colors that you can form from these 3 filters. And all these dots here, all the red dots have one particular redshift, and all the yellow dots have a redshift that's 1% different. And what you see is that this part of parameter space is completely overlapping. So at the level of 1% photometry, not 0.1%, but 1% photometry, galaxies like this, you simply cannot get the photometric redshift right. You simply cannot tell because you don't know, without a spectrum, you don't know how deep the absorption line is. All you know is where it falls in the color diagram like this. And so this is an idealized problem, but I'm pretty sure there are real degeneracies in real galaxy spectra which are at least as bad as this. And so the only way to fix this is to really know what the spectrum of your galaxy is. So you either have to go and do photometric redshifts, spectroscopic redshifts for a whole bunch of galaxies, which are accurately representative of these galaxies, or you have to add some extra physics or some extra information that tells you how deep this absorption line is or how high this break is going to be. Right? And that's not easy, because you want to do this at the sub-percent level. And for example, you can imagine any kind of metallicity trend with redshift. It's not at all unimaginable, which might give you a trend of these things from faint to bright galaxies, which means you cannot use bright galaxy templates to look at faint galaxies to sort this out. So this is very dangerous. Again, I'm not saying it's impossible, I'm saying it's something we really have to worry about in working with these surveys. Okay, just a quick slide to show that at the level of the data that we have at the moment, this stuff all works. This is a demonstration of how weak lensing tomography works. This is a single lens which gives a particular deflection angle here, and what you can see is that as a function of source redshift, the effect on the sky increases. This is the DLS over DS formula that we all know. Lensing is a measurement of angular diameter distances behind the lens. So for a long time there was a worry that systematic errors in shear measurements were too large to be able to see this effect directly. Tim Schabak showed in his talk that now, at least from Cosmos, which is a beautiful data set, we get the right kind of redshift scaling, and it is actually able to even yield some cosmological constraints that are plausible. So I'm not sure, if we didn't know what the cosmology had been, we would have really believed all this stuff completely blindly, but the fact that it gives what we now believe is the right answer, at least, is extremely encouraging. And it shows that at the moment, these kind of surveys are at the level where the systematic errors are under control down to the statistical level that the survey can have. But of course, we're thinking about scaling this up by a factor of 10,000 if we want to do a real space-based survey. And then I think we're still, the jury's still out whether we'll be able to do that. But for the moment, we'll always test it. And as Tim showed, you can already rule out most models which don't have an acceleration. Now, near future surveys for weak lensing and photometric redshifts abound. There's many plans. That's a huge investment of thousands and thousands of observing nights on many fancy telescopes all over the world. And so, so this is the bit which Yannick would have spent 10 minutes on probably, and which I'm going to give you all the chance to spend 10 minutes on at the end of my talk. With a CFHT lens, which is basically finished, and you've seen many talks of it and posters at this meeting. Pan-STARRS 1, Nick mentioned. Theirs is coming at the end of next year, I understand. I'll spend some time talking about the survey I'm involved in, which is KIDS and Viking, which is going to start next year now. I hope to convince you and myself. And there's many more things on the horizon with ever more ambitious facilities and telescopes. And then from space, there's also a lot of stuff going on. There's a number of deep patches already. It'll take a while before we get really much larger maps from space, just because doing this with postage stamps is very hard work. But there's a number of plans out there, including Euclid, of course, which is a big satellite, but also balloon-based things, which are sort of as close as you can get to space without going to space. Okay, so let me talk a little bit about the survey I'm most interested in. I'll try to highlight how we've tried to tackle some of these technical issues that came up in the requirements for being able to get weak lensing science out of such a survey. So this is Paranal. Paranal has the 4 VLT telescopes, but it also has 2 survey telescopes, VISTA and the VST. VISTA is purely dedicated to wide field infrared imaging, and the VST will be dedicated to wide field optical imaging. And both of those together will make one project called KIDS and Viking, which in total will be about 700 nights of imaging for weak lensing surveys. So they're part of larger surveys that ESO is planning. With the VST, there's a total of 3 surveys, a shallow one, a galactic plane one, and KIDS here, which you see has a strip on the North Galactic Equator, and not galactic equator, North Celestial Equator, and near the South Galactic Pole to be able to observe year-round. And these are the 2 patches that have been observed with the 2DF as well, so there's a lot of foreground spectroscopy already available. Then in the infrared, VISTA will have 6 surveys, and Viking is one of those, which covers exactly the same part. And then there's many deeper patches. matches in galactic surveys and so on. I won't talk about that.